Hello students, so in this lecture we will see how to develop a proportional feedback control model for lung mechanics. So the lung mechanics model we have already developed its electrical equivalent, so we will simplify that electrical equivalent little more and then incorporate the proportional feedback controller in that model, and we will see what are the advantages of that particular controller. So let us consider a simplified linearized lung mechanics model where R represents the combination of resistances of airflow in airways, the lung tissue resistance and the chest wall resistance. The C represents the combined compliance of lung tissues, chest wall and the airways. And the L inductor represents the fluid insertance in the airways. So the pressure developed at the different points in the lung models are: at the airway opening it is PAO, in the alveoli it is PA, and the atmospheric pressure or ambient pressure PO or P naught, and it is considered as the ground or the reference. So the objective of this analysis is to analyze the relation between the alveolar pressure PA and the applied pressure PAO at the airways opening. So if we apply the KVL in this particular loop, as there is only one loop, we will get PAO minus PO is equal to L dq by dt. So Q is the airflow volume or the current in the complete circuit, then RQ plus 1 by C integration of Q dt. So these are the potential drop across each element. So by applying KVL we know that the KVL states that the potential drop across each element in a closed loop is equal to 0. Further, the potential drop between these 2 points PA and PO has been estimated. So this is the potential drop between the across the capacitor. So it is written as PA minus PO is equal to 1 by C integration of Q dt. So to eliminate Q from both the equations, and by putting PO is equal to 0, we will get this particular equation. So from here, if we take the Laplace transform for this equation, we will get this equation, and from here we can estimate the transfer function for the given system. So PA is the output pressure and PAO is the input pressure. So the transfer function comes out as 1 upon LCS square plus RCS plus 1. So it is a second order system. Further, if we consider an alternative situation where we would like to able to attenuate the change in the PA as much as possible for a given set of lung mechanical parameter and a given imposed change in PAO in the clinical setting, it is desirable, since large fluctuation in PA can cause pulmonary barotrauma or damage to lung tissues. So in order to control PA, it is necessary to measure this variable and feed the measurement back to the controller. So in practice, this can be achieved by measuring the pressure in the mid esophagus with the use of an esophageal balloon. Since fluctuations in the esophageal pressure have been demonstrated to closely reflect the fluctuations in the alveoli pressure, that is PA. So previously, which we have estimated the open loop configuration, but as we earlier discussed, that A control mechanism is also required to uh, make the alveoli or the lung uh, safety, we can say. That is, if the pressure inside the lungs or the alveoli increase, there should be a corrective action taken by our lung mechanics. So for that we have to develop a closed loop model. So here we can assume a closed loop configuration. So we assume a closed loop arrangement where PA is measured and a scaled representation of this measurement is fed back and subtracted from the input PAO. This is clearly a closed loop configuration, and the type of control scheme is known as the proportional feedback, because we are using here a proportional variable constant which is multiplied with the output of the model and then fed back to the input side. So now we have to reanalyze the new block diagram to get the new transfer function. Here the transfer function can be written as the PA upon PAO, that is the input, minus the output of the system with a multiplication constant. So that is the only change which takes place in the transfer function. So if we simplify that particular transfer function, we will get this. So here we can replace this particular 1 by k from a constant, maybe lambda. So this complete model is the closed loop system model or the transfer function for the lung mechanics with proportional feedback control. So this is a second order system. So whatever transient response, steady state response, or the analysis we have done for any second order system, so that can be applied for this particular model also. And we can estimate the dynamics of the system for any given input, a standard input, that is the impulse input, the step input, the ramp input, or the parabolic input. So this is the model for lung mechanics with proportional feedback controller.